All right, so today we are going to start talking about differential amplifiers. Actually, before we do this, I got a homework assignment up and I solved them and all that kind of stuff this weekend on current mirrors and all that kind of jazz. So that's up. I started uploading some files for your design project, so they'll be in the electric VLSI thing. Right now, the only thing that I have written up is formal instructions for downloading and installing the, I use the word program very loosely. It's literally just a .jar Java file. And I'm writing out the instruction for you guys. So your first project, as it were, is just going to be to follow along with me and make a simple inverter. Okay. We're going to use that for a couple of things later on. And for those of you that go on to take the integrated circuits class next fall, you'll use it for large scale VLSI design and all that kind of stuff. So I'm just trying to introduce you to it in this quarter. I anticipate I will have my solutions made for the homework assignment on cascode current sources and cascode amplifiers by the end of tomorrow. So that homework assignment, I'll try to push that out tomorrow, and it'll be due a week from tomorrow on Tuesday to give you guys plenty of time to work on that and still be able to enjoy your Easter break without putting up with too much of my bullshit. So that's the plan for all of that kind of good stuff. All right. Yes. So I found out after 4 years of using Zoom, let me double check and make sure I'm recording this, but I feel like I am. You've got me nervous about it. But after 4 years of using Zoom, I found out that you can actually hide that stupid bar by pressing that button so that it doesn't get in my damn way all the time. I wish I had known about that much earlier, but anyway, so I am recording. Just doesn't look like it because that stupid thing isn't in the damn way anymore. All right. Okay, so like I said, we're going to be talking about differential amplifiers, and this is the last large topic that'll be on your first exam, and I've got roughly 5-ish lectures prepared for this. So, to this point, all of the transistor amplifiers that we have analyzed have been single-ended amplifiers, meaning that they had a single input terminal and a single output terminal. So realistically, we could treat them as a simple, hesitate to even use the word circuit here, but something like this, where we have an amplifier block containing the characteristics of our transistor amplifier. So voltage gain, input resistance, and output resistance. And if we apply some input signal to our amplifier, so this is our signal voltage V sig. Here's our output voltage. So if we put a small sinusoidal signal in, we expect to see a large sinusoidal signal out, where the magnitude of that output signal is dependent on the voltage gain. So this could be representative of any common emitter, common source, common base, common gate, common collector, common drain amplifier, doesn't particularly matter. Input signal, output signal based on voltage gain. Okay. So while a amplifier or single-ended amplifier like this is useful for a lot of applications, it does have drawbacks and limitations, particularly if we have some sort of noise or unwanted perturbation in our system. So if we had something like this, where we have our simple amplifier circuit, But now, instead of just a nice, clean input signal V sig, where we have a simple sinusoid, we also throw some noise on top of it. What do you think is going to happen? Well, we are going to get our nice clean output signal, but superimposed on top of that, we're going to see that noise gets amplified as well. So one commonly used method to suppress the noise or suppress the effects of the perturbation is to use a differential amplifier. So a differential amplifier is fundamentally different than a single-ended amplifier in as much as it is designed for multiple input signals. So we might have some input signal here. Let's call it VN1, and some input signal here. Let's call it VN2. And then we're going to have some output signal here, Vout1, and some output signal here, Vout2. This is the voltage gain of our differential amplifier, and typically we call one of the terminals a non-inverting terminal and the other one of the terminals an inverting terminal. So we are slowly working our way towards understanding what the hell is going on inside an op amp, is effectively what's happening here. So we can literally think of this as kind of like two single-ended op amps, but our output signal could be taken as the difference between those output terminals, meaning that if the noise were applied to both terminals equally, and we took the difference of those outputs, the contribution of the noise would cancel each other out. So if we had our input signal 2 as just noise, and this guy up here was V sig plus noise, our output over here would just be AV times V sig effectively. So whenever we apply the same signal to both input terminals of our op amp, we call this a common mode signal. So and the signal that's applied to only one side effectively is what's called a differential mode signal. So let's clearly define what those things are here. So common mode and differential mode signals. So our differential signal is simply the difference of the two input or output signals. So here I'm going to have VID. So let me explain something really quickly here. The I is for input and the D is for differential. So VID would be our input differential voltage signal. And that is literally just going to be the difference between VN1 and VN2. And then our output differential mode signal, VOD, is simply the difference between Vout1 and Vout2. So pretty easy to understand what's going on with our input and output differential mode signals. We just take the difference of the input signals, take the difference of our output signals. Nothing particularly wild or crazy there. Our common mode signal is the average of the input or output signals. So our input common mode signal for a differential amplifier that has two inputs would simply be VN1 plus VN2 over 2. And our output common mode signal, VOCM, would be Vout1 plus Vout2 over 2. And so what we can do is we can actually rearrange these relationships, all four of these relationships, and what we could find, and I'll do that over here, is that VN1 can be decomposed into a common mode signal and a differential mode signal, where we would have VICM plus half of VID, and our input signal VN2 could be decomposed as VICM minus half VID. And it's this approach that we're going to wind up using, particularly when we start looking about how this guy works as an amplifier. Okay. So what it's really going to allow us to do is effectively choose, like we could say that there's only a common mode signal on one input and all of the differential mode signal is applied at the other input, or we can split it up if that's what winds up making the math easier. So we're going to move that differential mode signal effectively around to see how things work. All right, so I want us to look at a circuit. Yes.
Explain what I see in standard code.
Input common mode, and OCM is output common mode. When we start talking about common mode rejection ratio and differential to common mode gain conversion and all that kind of stuff, we're going to get ridiculous with the subscripts, but I'll make sure to pay more attention to that. It'll be a few days before we get there, but there's going to be lots of little subscripts that we're going to be dealing with for this month. Okay. So I want us to look at a circuit. Let's say that we have simple step down transformer. So here we have 120 volts RMS at 60 hertz. We have a turns ratio of N1 to N2. And then over here on this side, we have some step down voltage. And this step down voltage is fed into a bridge rectifier. So this is actually an IC representation of just 4 diodes connected in a Wheatstone bridge configuration like we did for rectification in electronics 1. Okay. And then here we have our smoothing capacitor. Let's call it C1. And then I'm going to give myself enough room here. So up top, this is our supply voltage for an electronic circuit, which we know should be VDC plus some amount of ripple voltage. And then over here, we'll have a simple common emitter amplifier. So let's call this for now RC1, V out 1. Here's transistor Q1. Here's VN, here's CN, and I'm just putting 2 bias here because we're not going to worry about that too much. So here we have a single-ended amplifier connected to a power supply that is for sure experiencing some amount of perturbation because there's a ripple voltage involved because we've rectified an AC voltage to give us a DC. So what would we expect to see here on our output voltage? We're going to see some noise. We're going to see some distortion because of the power supply ripple, right? So how might we convert this single-ended amplifier into a differential amplifier? Well, what we're going to do is we're going to add another common emitter amplifier. Where this resistor RC2 needs to be matched to RC1. If it isn't, we'll talk about what that entails when we get to my, I think it's called like advanced topics for differential amplifiers lecture, whatever, in about a week and a half or whatever. But we'll see what happens when we don't match our resistors. We'll also see what happens if we don't match our transistors, which is a possibility. Like so. And then this guy is effectively connected to bias as well. So looking at this thing, our output voltage for V out 1 should just be our amplified input voltage plus our DC offset, which would be VCC minus RC1 IC1 V out 2 because we don't have any input signal that we're amplifying on that side, right? The base is connected effectively just to our bias network or a DC network. We have VCC minus RC2, IC2, and then our differential output is just V out 1 minus V out 2 should come out to just be AV times VN if Q1 and Q2 are matched and RC1 and RC2 are matched. So we no longer get any distortion. We can actually expand on this further, and we'll do that in a little bit. So we set up this whole second amplifier here to effectively minimize the effects of perturbation. Another way that we could minimize those effects of perturbation would be by current source biasing Q1 and Q2. So this is what our true differential pair amplifier is going to look like. Let me go ahead and do this on a separate page. So the BJT differential amplifier. All right. So from here forth, we are going to assume that our RCs are going to be of the same value. So I'm just going to use RC to label both of them. So here's V out 1. Here's transistor Q1. Here's our input voltage VN1. And then over here on this side, I'm going to effectively just duplicate this circuit. Here's RC, V out 2. VN2. And now what I'm going to do here is I'm going to put what's called a tail current in. Okay. I'm doing it as a ideal current source right now, but as you guys should be aware by this point, realistically, that's going to look like a current source or a transistor current source, probably a cascoded transistor current source there. And we'll talk about that in a bit. So let's talk about how this circuit works as a whole. So I want to identify a couple of things here. So the current that's flowing through our resistor RC is IC1 on this side. The current that's flowing over here, we'll call it IC2, which reminds me that I need to label this as Q2. And this is VCC. This current right here is IE1. And this current right here is IE2. So I want us to answer a couple of questions qualitatively to figure out what's going on, and then we'll throw math at it to get much more specific. Okay. So my first question is, if a common mode signal is applied to the inputs, what happens to IC1 and IC2? So if our differential input signal is effectively zero, so that we only have a common mode signal applied at our inputs, what do you guys think is going to happen? Okay. So first thing that we can see is that if we apply the same voltage to VN1 and VN2, this base emitter voltage VBE1 and this base emitter voltage VBE2 have to be the same, right? So what implications does that have? Well, IC1 and IC2 also have to be the same, right? If IC1 is equal to IC2, our emitter currents also have to be the same. And according to Kirchhoff's current law, they must both be equal to IEE over 2. What would our output voltage be? Or what would our differential mode output voltage be? 0. So effectively, we don't amplify common mode signals with a circuit like this. Yes. So if we apply the same, literally the same voltage to VN1 to VN2, no difference between them whatsoever, that is applying a common mode signal. The same two identical voltages on the same voltage applied to VN1 and the same voltage applied as VN2. So that's what's forcing VBE1 to be equal to VBE2, which in turn makes IC1 equal to IC2. Since our collector currents is equal, our emitter currents have to be equal, and they're both equal to 1/2 IEC. So what we're going to be getting towards effectively is we're going to see how this differential amplifier effectively, from a DC standpoint, is just a current steering device. And that'll make more sense here in a moment. Okay. So we've answered our first question. So now let's say we have a second question here. What happens if VN1 is greater than VN2? Or another way to put this would be our input differential voltage is positive. So if VN1 is greater than VN2, then what's the relationship between VBE1 and VBE2? VBE1 would be greater than VBE2. Okay. So VBE1 would be greater than VBE2, which in turn means that IC1 would be greater than IC2. Which in turn means, sorry, that should be an I. IE1 is greater than IE2. So if the input voltage on transistor Q1 is larger than the input voltage on transistor Q2, then Q1 starts carrying more of the current. So if we apply voltage on the left-hand side that we don't apply on the right-hand side, we drive more current through the left-hand side. The total amount of current that can ever be driven, though, is just IEE. So we are steering more current to the left-hand side of the circuit. What's going to happen to the output voltage? So let's make an assumption here. We're getting a little bit ahead on the math. But let's say that we are applying more than 5 thermal voltages on VN1. Right? So our input differential voltage is large. Effectively, all of the current is going to flow, or all of our tail current IEE is going to flow through transistor Q1, and next to none of our current would flow through transistor Q2. So what would our output voltage on Q2 be if IC2 were 0? So if there's no current flowing through that through that resistor RC, there's no voltage drop across that resistor RC. And so on that side of things, our output voltage would actually be VCC. Right? So it's going to pull that output voltage high, and the other transistor is going to drive that output voltage low. So we're going to wind up getting some small number minus VCC. So we're going to wind up having a negative output voltage. So we could say that Vout1 will definitely be less than Vout2 in that case. So our output differential mode voltage is a negative one. What happens if VN2 is greater than VN1 or VID is less than 0? Effectively the exact opposite, right? So VBE2 will be greater than VBE1, which means IC2 will be greater than IC1, which means IE2 will be greater than IE1. So transistor Q2 is carrying more of the current, so its output voltage is being driven low. The output voltage of transistor Q1 is being pulled high, and when we take the difference of those things, our output differential mode voltage is going to be a positive one. So let me write all that down. VBE2 will be greater than VBE1, which in turn causes IC2 to be greater than IC1, which in turn causes IE2 to be greater than IE1, and Vout2 will be greater. Sorry, Vout1 will be greater than Vout2. So now let's formally throw math at this and prove that that's how things are going to work. Okay. So we have a basic understanding of how things should shake out. Now we're going to be a bit more granular in our approach. So to facilitate this, I'm going to redraw my circuit. Here's RC. Here's V out 1. On this side, I'm going to apply some positive input differential mode voltage VID over 2. Here's transistor Q1. On this side, I'm going to have negative VID over 2. Common mode portions just cancel each other out. In this case, the common mode portion would effectively be 0 for what it's worth. And let me specifically draw some things. So here's IC1, IE1, IC2, IE2. I don't know why I keep forgetting to label transistor Q2. VBE1 and VBE2. And just to be very, very clear, our goal is to get our output differential mode voltage as a function of our input differential mode voltage, which as an intermediate step is going to require us to find our output differential mode voltage as a function of the change in the collector currents on both sides. Okay. So let's define V out 1. Formally here, okay? So as a DC signal, what should V out 1 be? VCC minus IC1 RC. V out 2 would be VCC minus IC2 RC. We know that IC1 and IC2 probably aren't the same thing because we have two different voltages applied at the inputs on either side, right? So from this, our output differential mode voltage, V out 1 minus V out 2, is going to look like negative RC times IC1 minus IC2, or negative RC times the quantity delta IC. So now, seems like our goal is to figure out how the change in our collector currents is influenced by our differential mode input voltage. So let's sort out how that works. Okay. So what I'm going to do is I am going to write a Kirchhoff's voltage law equation. So I can say that my input differential mode voltage over 2, VID over 2, so that's the potential between here and ground, just to be very, very clear, is going to be equal to the voltage drop VBE1 minus the voltage VBE2 minus VID over 2. Are we okay with that? So just to be wildly clear, this is the path that I have taken. Started from here, went this way, and then down to this ground. So starting from ground, ending at ground, and then moving the VID2 to its own side of the equation. That's what we get. All right. This can hopefully very obviously be arranged to find that our input differential mode voltage is simply the difference between VBE1 and VBE2. Well, we know how to express VBE1 and VBE2 in terms of our collector currents, because we know how BJTs work, right? So we know that IC1 is equal to IS times the exponential of VBE1 over VT, and we can rearrange that to get effectively VBE is equal to VT times the natural log of IC over IS. So from here, we could say that our input differential mode voltage, VID, is going to be VBE1, which can be expressed as VT times the natural log of IC1 over IS minus VT times the natural log of IC2 over IS. Anybody got beef with that? Okay. What do we know about natural logs and subtracting things? Combine them, right? Absolutely right. So it would be the natural log of this guy divided by this guy. And since we're dividing by this guy, it's the same as multiplying by that reciprocal. So the IS's are going to cancel each other out. And we wind up getting VT times the natural log of IC1 over IC2. We all seem to be okay with that. So now, let's write a Kirchhoff's current law equation at that node. So we would have our tail current, IEE, is equal to IE1 plus IE2 And I can express those emitter currents in terms of our collector currents, right? Now, usually, we do this in terms of beta, where we would have beta plus 1 over beta. But that's going to make things cumbersome. So I'm going to ask you guys to recall something that we literally haven't used since I introduced it. Let me put it over here. Alpha was equal to beta plus 1, or excuse me, beta over beta plus 1. Right? We use this relationship extraordinarily briefly back in 335. It's just going to give me less to carry along and screw up the algebra with. Okay. So that's going to look like I can rearrange this to say effectively that alpha IEE is equal to IC1 plus IC2. So I'm going to put some boxes around things, right? So we have this expression right here that relates our input differential mode voltage, our thermal voltage, and IC1 and IC2. And then we have this expression right here that relates alpha, a known quantity, our tail current, IEE, and IC1 and IC2. So we have two equations involving IC1 and IC2. So effectively, we can solve this system with some algebra to see what shakes out here. So I'm going to start with my alpha IEE equation, right? So alpha times IEE could be written as IC2 times 1 plus IC1 over IC2. Are you okay with that? I've just factored out an IC2 from that expression. Well, now that I have an IC1 over IC2, and I can manipulate that top relationship that I circled in blue. And so that's going to look like IC2 times 1 plus the exponential of VID over VT, so that I can now say that IC2 is alpha IEE divided by 1 plus the exponential of VID over VT. Anybody got any problem with that? We can do something similar. We could say alpha IEE is equal to IC1 times 1 plus IC2 over IC1. And that would mean that we would have IC1 times 1 plus the exponential of negative VID over VT. From this, IC1 is going to be alpha IEE divided by 1 plus exponential of negative VID over VT. Okay. So let's pause right here and look at a couple of things. So let's say that our input differential mode voltage were 0. What would IC2 come out to be? So it'd be alpha IEE divided by 1 plus EXP of 0. EXP of 0 is 1. So alpha IEE over 2. So a little bit less than exactly half of our tail curve. Very similarly, we would see that IC1 comes out to be literally the exact same thing. So when our input differential mode voltage is 0, both transistors carry the exact same amount of current. So the math here matches up exactly as to what we would expect based on our qualitative analysis earlier, okay? Now let's say that VID is a positive quantity. If VID is a positive quantity, where it's, let's say, significantly larger than VT, then IC2 is going to approach 0, and IC1 is going to be something large, right? Because E to the negative something large, this guy's going to go to 0, and we're going to see that IC1 approaches alpha IEE. When our input differential mode voltage is a negative quantity, the exact opposite is going to happen. So far, the math bears out to match exactly what we have described previously. Okay, so now here's where the math gets a little gross. Delta IC is just IC1 minus IC2. That's going to be alpha IEE divided by 1 plus the exponential of negative VID over VT minus alpha IEE divided by 1 plus EXP of positive VID over VT. Okay, nothing bad there. Now, we're going to factor out effectively a common factor of EXP of negative VID over twice VT from both sides. So on this side, we're going to have alpha IEE divided by the exponential of negative VID over twice VT. And then here, we're going to have EXP of positive VID over twice VT plus the exponential of negative VID over twice VT. So just to be clear, when I multiply these two guys together, I get the exponential of 0, which is just 1. When I multiply this guy by this guy, those exponentials add together, and I just get negative VID over VT. Doing something similar on the other side, I'm going to have alpha IEE over exp of positive VID over twice VT times exp of negative VID over twice VT plus exp of positive VID over twice VT. Close that guy off. And now I can see that effectively alpha IEE over exp VID over 2VT plus exp over negative VID over 2VT is a common term on both sides. So that's going to look like alpha IEE over the exponential of VID over 2VT plus, sorry, don't need the parentheses there, exponential of negative VID over twice VT. And then that whole thing is getting multiplied by one over the exponential of negative VID over 2VT. I'm going to leave myself some room so that we can play with that in a moment. And then 1 over exp of positive VID over 2VT. All right. So I'm going to multiply this guy by this over this, effectively just a fancy one. And I'm going to multiply this guy by this over this. Which is going to make that one look like exp over VID over twice VT. Here I'm going to have exp negative VID over twice VT. What's this denominator look like? 1. What's this denominator look like? Also 1. So effectively, I have this minus this over this plus this times alpha IEE. So exponential of VID over 2VT minus the exponential of negative VID over 2VT divided by the exponential of VID over twice VT plus the exponential of negative VID over twice VT alpha IEE. Grayson here? There he is. Think the math club, what's that? I believe it's a hyperbolic tangent. Alpha IEE the hyperbolic tangent of VID over twice VT. So all of that terrible math just to get to hyperbolic trig identity. Using that, we can recall from the beginning that our differential mode output voltage was negative RC times the change in our collector current, or negative alpha RC IEE times the hyperbolic tangent of VID over twice VT. I want to be clear here. This is the relationship that tells us what our DC operating point is for our output voltage. All right, this is the stopping point for today. So what we're going to do on Wednesday's class meeting is we are going to do something similar for MOSFETs. So we're not going to worry about the small signal analysis until we have an understanding of what the large signal analysis is for both, because the small signal analysis is going to be effectively the exact same thing. So for what it's worth, I think the MOSFET large signal analysis is even grosser. Yeah. Sure. Like the or the let me scroll up here and make sure. So we're looking at this thing here. So it's really the ripple voltage that's messing things up, right? So it depends on what you mean by the transistors don't work. Like realistically, we're just trying to minimize the chance that they get pushed out of the active mode of operation, right? So effectively, that ripple voltage is going to be constantly increasing and decreasing our headroom that our output signal is allowed to occupy. Because remember that if it dips too low, we're pushing our transistor out of the forward active region and into the saturation region. So like, if we were dealing with, say, let's say this guy right here, we're 5 volts, and we had plus or minus 1 volt of ripple, that's pretty darn gross. If we were dealing with plus or minus 0.1 volts of ripple, that's not going to have a huge effect. So this thing right here, if you notice, like typically speaking, we would have a resistor in parallel with a capacitor to smooth out things. This transistor circuit is playing the role of the resistor. I'm sorry, what? Yeah. So we're using a bridge rectifier because we can usually get a small amount of ripple without having to use a huge capacitor there, as opposed to a simple full wave rectifier. Yeah. Is it cheaper to use EJTs? I don't fully understand the question. No, okay, so you're mixing up the cart and the horse here. everything to the left of this is just the supply for the amplifier circuit. The amplifier circuit is what we're interested in. All that shit to the left is just how we are establishing VCC. Yeah. So we want the BJTs there because our goal is to amplify some signal. This is just a practical way of doing it because this is what the internal circuitry as a loose approximation of what a DC power supply actually is. It takes AC from the wall, steps it down to some allowable level, much less than 120 volts RMS. And then we use a rectifier circuit to make that approximately DC. But now we've run into the point where we're constantly perturbing our supply voltage for our amplifier because inherently converting AC to DC gives us some amount of risk. Yeah, so you're looking at it the wrong direction.